Um, okay. So inspiration here, inspiration is an active process. Inspiration is an active process. Okay. And an active process is require the phrenic nerve. The phrenic nerve is part of the um, cervical plexus. And it's going to innervate the diaphragm. Okay, it's part of the reverberation. It's going to innervate that. And when the diaphragm contract, is flattened like this. It's flattened, so that now this right here, the thoracic volume decrease. Right. Sorry, thoracic volume increase, which meaning that the pressure will be decreased. That's the Boyle's law, right? Pressure is inversely proportional to volume. So if the volume increase, the pressure will decrease. And so air, the atmosphere here, air, then can rush in like that. So again, I was going to say that what is the primary force that allows air to go in is the atmosphere is the primary force. Okay. So if you're in space, you don't have the atmosphere. It's harder to breathe, right? Even if you go up the mountain, it's harder to breathe because the pressure is very low. Okay. So that's inspiration. Expiration is a passive process. Okay. You see, expiration is a passive process, which meaning that you stop the phrenic nerve from working, and the diaphragm now bounce back. Diaphragm bounce back. The air just basically will go out. Okay, will go out. So over here, over here, sorry. So in the exhalation or expiration, the same thing. Expiration is going out. Is passive process. Right? And by passive process is that you don't, the phrenic nerve stop, this thing bounce up, the volume here, volume increase. Sorry, thoracic volume smaller, volume decrease, pressure increase. Right? So again, you can see the pressure inversely proportional to volume. If these things drop, right? So you're dividing by a smaller number, this will be increased, and then air just flow out like that. Okay, so inspiration, you can see here is that in the lung, 760 millimeters of mercury, and innervates this diaphragm contraction. It goes down to 760 or 758, 756, and then because it's lower, air would just go in. Okay. Now, if I give you a, if I ask you to take in as much air as you can, like this, so we call that, it's known as forced inhalation. Forced inhalation. If you could just take in a lot of air, right? So what you want to do is that you want to make the rib cage even bigger, right? So the pressure is even lower, so then you can just bring it in. And so if you wanted to raise the rib cage, you needed the pectoralis minor, this one here, to raise it. Very important to know. So remember this, EI versus IE. It's the same, right? But in the inhalation, you require the external intercostal muscle. Intercostal muscle. Right? So you can see here is that in the external intercostal, it's going to, the external outside is going to raise up the rib cage. Right? So in the inspiration, we require external intercostal. Right? Now, IE, why does this thing work? Okay. So internal inspiration require external intercostal. On the other hand, exhalation which is E, will require the internal intercostal. Okay, internal. So the internal costal muscle. So then the muscle inside is going to compresses down on the rib cage, right? So if I give you a balloon to blow up, we call that forced exhalation, right? You want the rib cage to go down. You might want it to cause your abdominal muscle to contract like this. So you want to bring the diaphragm all the way up again. So the volume is very small, but the pressure is very high. So it can blow it out. Okay. All right, so here's all the major events that occurs in inspiration. You can read that. The important here is phrenic nerve, contract the diaphragm's lower intravalvular pressure would decrease, air just goes in. Intrapulmonary pressure means the pressure inside the lung. Intrapleural pressure entices the pleural. This is pretty much very similar in a way. Transpulmonary pressure, this is important. This is between in the alveolus and in the pleural membrane. The transpulmonary pressure typically is about 3 millimeters of mercury. The different, which helps the lung to inflate. If this transpulmonary pressure is equal to 0, right, then you have collapsed lung. So there's nothing that helps the lungs to inflate. Another important thing is inflammation. Inflation of the lung is aided by warm air, right? So you can say, which gas law that says that temperature is proportional to volume, increases the warming of the air? What gas law is that? Do you remember? Temperature is proportional to volume. Warming of the air help the lungs to inflate. It's the, yeah, good. It's Charles' law. Good. Thanks, Rupa. You got 2 right today. All right, so here's some more title. The normal breathing that you see that goes inhalation, exhalation, inhalation, exhalation, inhalation, exhalation. This is known as tidal volume. Okay. And the tidal volume, good number to note, is about 500 ml. So that's when you're breathing, you take in about roughly 500 milliliters of air that goes in and out, tidal volume. We're going to talk about that a little bit. So just finish up with expiration, right? You want it to make the rib cage lower. You will require the abdominal muscle, right, to contract to bring it up, as well as the internal intercostal. In the forced exhalation, you require um, okay, maximum expirations are called forced exhalation. You require here, okay, internal intercostal. So again, E, I, right? Not I, inhalation require external intercostal. So I, E, E, I, okay? Keep that in mind. And expiration, actually, you can also say that this is a passive process. Unless it is in a normal breathing, but in a forced exhalation, then you require the abdominal muscle to contract, to bring up the diaphragm way up more. So you can see here that intrapulmonary pressure, 760 with 1 atmosphere. In the pleural, it's lower, right? So this is known as transpulmonary pressure. And it changes accordingly. So even if you inhalation or exhalation, the transpulmonary pressure is going to be the same, which is about 4. Okay. But if there's no transpulmonary pressure, then that leads to collapsed lung. All right, so these are the number, really nice number you guys need to know, and I'm just going to show you here. Okay, these volume of air that you take in, like this is vital capacity, or this is known as tidal volume, and a tidal volume is about 500 ml, okay, liters of air. Now, if you just normal breathing and you just take in as much air you can, normal breathing, as you can, this is known as inspiratory reserve volume. So the inspiratory reserve volume is about 3,000 milliliters. Okay. Now, just normal breathing, and you say, oh, blow out as much air you can. This is known as expiratory reserve volume right here. And expiratory reserve volume is about 1.2 or 1,200. Yeah, 1,200 to 1,500 milliliter of volumes of air. Here's the key word, all right? Now, if I ask you to take in as much air as you can and to blow as much as you can, this is known as vital capacity. So vital capacity is to take in as much air as you can. Vital capacity is to take air as much air as you can and to blow out as much as you can. This is a vital capacity. And for most people, it's about 4,700 ml. Okay. So that's including 3,000 for inspiratory reserve volume, plus 500 tidal volume, and plus 1,200 expiratory reserve volume. That's vital capacity. Now, no matter how much air that you take in, how much air you blow out, there are also some remain. This is known as residual volume. And residual volume is about 1,300 ml. Okay. So between 4.7, which is 4,700 liter, and 1.3 liter for residual volume, you get 6 liter. And this is known as the total lung capacity. You can see here. Okay. This is TLC, tender loving care, or total lung capacity is about 6 liter. So, just like cardiac output is equals to heart rate time stroke volume, we want to see how well the lungs are working. So this is defining as minute ventilation. The minute ventilation, right, is equals to the tidal volume, which is equals to the tidal volume, which is 500 ml, time the respiratory rate, which is usually this is 500 ml, and respiratory rate is about 15 breath typically, right? And so you have their 75 liter, sorry, 7.5 liter or 7,500 milliliter per minute, roughly the total lung capacity within that 1 minute. Now, knowing that because when you inhale in 500, when you're inhaling in 500 milliliters of air and then you exhale 5, so this is inhalation, exhalation, inhalation, X100. This is your tidal volume. And tidal volume is 500 ml, right? But this is going to occupy from the nasal cavity to the pharynx, to the larynx, to the trachea, to the bronchi, right? All the way to the terminal bronchial, okay? all the way down to the terminal bronchial. There's no gases exchange at all. So air is occupied in this, but there's no gas exchange. We call that a dead space. It's a dead space. So only, the dead space there is estimated to about, 350 ml, right? So of that 500 that you take in ml, it's estimated about 150 ml are the gases that is finding starting from the respiratory bronchial, respiratory duct, and alveolus that allows us for the gases exchange to occur. And so the alveolar ventilation rate is a better indicator of lung capacity, is because it takes the tidal volume minus the dead space, okay, and then times the respiratory rate, and that's it. Because it's tidal volume minus the physical dead space that give you multiplied by the breath rate. So that's the alveolar ventilation rate. You can see. I'll show you that. Okay, so non-respiratory movement, I'm not going to talk about too much other than that air involving coughing, involving sneezing, hiccuping is that, these basically cannot control the diaphragm. In other words, diaphragm contracts spasmodically. Yawning, that's actually yawning is very social behavior. You know that. So that if you see someone yawning, most likely you're going to copy that. So it's like, right. I bet you one or two of you is following me yawning. It's a very social behavior. And because of the air going through, it causes that vibrations of the vocal cord is important for speech. And again, where do you find the respiratory center? At the medulla oblongata is where you find the respiratory center. In there, you have two groups of neurons. Okay, we call it the dorsal respiratory group and the ventral respiratory group. Now, which one of these is involved in normal breathing, right? Breathing the regulation is a little bit complicated. Is because inhalation, if you take air in, right, you have to inhibit the exhalation. And if you're taking air out, you have to inhibit the inhalation. Okay? So there's normal respiratory rate and there's a forced respiratory rate as well. And the guy that is controlling the conductor that sits above all that is the pons. Okay, the pons here. It's called the pontine regulation, which is it's their pontine regulation is to say, okay, if you want forced inhalation, you have to inhibit the normal breathing, and right, because you have to coordinate this event, because and inhalation is that inhalation and exhalation has to be inhibited. of each other, because you don't want to breathe into something go that kind of breathing. It should be inhalation, exhalation, inhalation and exhalation. Okay, so your job is depends on the book, but the dorsal respiratory group. Okay, I'm going to call it the dorsal respiratory group is involving the basic rhythm. Okay, whereas the ventral group is involved in forced inhalation. And both of these, if you want forced inhalation, you have to inhibit this. And if you want normal breathing, you have to inhibit this. And so the pontines, the pons that regulates this. But where do you see the dorsal respiratory group and the ventral respiratory group is at the medulla, oblongata. That's the respiratory center. Okay, there are other factors that regulate this respiratory, particularly the also baroreceptor in the aortic as well as the carotid artery body there, which is senses into the medulla oblongata. And there are not only just the baroreceptor, but there's also chemical receptor that sensing if that is too much CO2, then we're going to increase its respiratory rate, for example. Okay. All right, so we're going to just do a little bit about physiology. Respiratory membrane we talk about, you guys need to know that. All right. Next 20 minutes or so. In this process, we call it the, see how CO2 is dumped and oxygen is loading. This is part of what we consider as a external respiration. CO2 unloading, oxygen is loading. Okay. Now, partial pressures of oxygen in the lung is about 152 millimeters of mercury, based on that 18%, 20% partial pressures of oxygen in the partial pressures in the atmosphere. But because the oxygen, as you get in deeper into the respiratory tract, is going to join with more CO2, so that the partial pressures of oxygens in the lung is about 100 millimeters of mercury. But it's sufficiently high so that allows us the oxygen to go in. Okay. Now, the oxygen that you see in our body is carried in two places. Where are they? Most of the oxygen is carried as oxyhemoglobin. So in other words, what you see is that oxygen is going to bind to deoxyhemoglobin to become this. Okay. This is known as oxyhemoglobin. That's the oxyhemoglobin. And then this will tie up with that will be water, for example. Okay. So in the blood, soluble oxygen is very low. All right. So in the blood, most of the oxygen is carried as oxyhemoglobin, and soluble oxygen is very low. It's low, but there is there. Oxygen is low. Okay, so most of our oxygen in our body is carried as oxyhemoglobin. A little bit of it as a gas, right, in the plasma. On the other hand, CO2 is found in three forms. Okay, most of it, 70% of CO2 in our body, CO2 is carried. I'm sorry, that's CO2 is carried as bicarbonate. Okay, about 20 or 25% of CO2 is tied to hemoglobin as well. Hemoglobin. So we call that as carbamino. Hemoglobin, and then very little as a soluble CO2 CO2 gas. Okay, so make sure you note that in our body, right, the bulk of CO2 is tied as bicarbonate. And bicarbonate is that we already know that's mean that water, right, plus carbon dioxide. This is another functions of the blood. Will give you carbonic acid. Carbonic acid is broken down to, that's a 3, hydrogen ion, and this guy right here, bicarbonate. So when you're expelling the CO2, you're taking from this bicarbonate. If you have too much CO2, it's going to be tied as bicarbonate. Carbon dioxide can also couple with hemoglobin. So then it becomes this. And water. So in this case, this is known as carbaminohemoglobin. Carbaminohemoglobin. And of course, soluble CO2, soluble CO2. So one important thing is that in the venous return, the partial pressure of CO2 is very high. It's 45 relative to in the lung, it's 40. So then CO2 is unloading. This is the opposite of it in true. All right, so this is basically to show you the similar thing. I don't know if you have this. Okay, so this is part of, we'll call it internal respiration. How much time? Okay, I still got 10 more minutes. In an internal respiration, the partial pressures of CO2 here is high. Okay, the partial pressure of CO2 here is 45. You see that? So, but the partial pressures in the blood, oxygenated blood, partial pressure of CO2 is 40. So CO2 will enter into the blood. So we call that in the internal respiration, CO2 is loading. The oxygen in the blood that is become oxygenated, partial pressures of oxygen in the blood is about 90 when it reaches here. Okay. For partial pressure of oxygen is 90 millimeters of mercury. It's still sufficient high, but the partial pressures of oxygen in the tissue is about 40. Okay. So then you see that oxygen will leave, right? Like this, oxygen unloading. Here's a very important thing, which I'm going to draw out this area. You can bear with me. Now, okay, as part of the internal respiration, so here you get this red blood cell. Now, partial pressures of CO2 is very high. CO2 ultimately will get into and reacted with water to become bicarbonate. And the bulk of CO2 is carried in this form as bicarbonate, right? In the plasma themselves. Or what happened is that the significance of the red blood cell is that this bicarbonate will enter the red blood cell, right? This is a negative charge, and as consequently, CO2 will leave. This is known as the chloride shift. So note this, and you might have to do this, listen to this recording again. But in the internal respiration involving the chloride shift, okay, bicarbonate enter, chlorides leave. And when the bicarbonates that is enter, what you can see. No, sorry. It's the, let me erase this. All right, let me do it one more time. In the internal respiration, so CO2 is high here. CO2 can get into the blood, and that CO2 can convert it to bicarbonate. Okay, CO2 can react with water. I'm going to forget it. I'm not going to put down, okay, why not? Okay, carbonic acid breaks down to bicarbonate. Bicarbonate and hydrogen ion. Now this reaction is very slow. Okay. Now you need an enzyme, and this enzyme is known as carbonic anhydrase. This enzyme is known as carbonic anhydrase. Okay. If you have this enzyme carbonic anhydrase, it's going to make this reaction go really fast. It's going to make this reaction really fast. And guess what? That is the significance of the red blood cell. Okay. So what happened is that as the CO2 enter, it actually get into the red blood cell. CO2 with water again, right? Get carbonic acid, and it breaks down to the bicarbonate. Okay, sorry. Bicarbonate is negative plus hydrogen ion. Right. So in the internal respiration, the red blood cell is in fact making a lot of bicarbonate, and bicarbonate then leaves the red blood cell. Bicarbonate exit the red blood cell, and the chloride will comes in. So that's a chloride shift. Bicarbonate leave, the chloride will comes in. Okay, so there's an enzyme. The red blood cell have this enzyme, carbonic anhydrase. Okay, and it catalyzes the reaction to make into bicarbonate. So in the internal respiration, the bicarbonate leave and the chloride comes in. It's a shift. But notice that the red blood cells then has a lot of hydrogen ion. So it turns out that oxyhemoglobin, right here, if there is a lot of hydrogen ion, it could react to that. So in other words, oxyhemoglobin, this is oxyhemoglobin. If it has hydrogen ion, it will bind to hydrogen ion with higher affinity. In doing so, what you're going to see is that it's going to form this. This is now is known as hemoglobin binds to hydrogen ion. So this is known as deoxyhemoglobin. This is known as deoxyhemoglobin, right? Now, what it does then with the hydrogen ion is going to kick out that oxygen, and it kick out this oxygen like this, right? So oxygen is very high now inside the red blood cell. Inside the red blood cells goes into the blood, and it leads to oxygen unloading, CO2 loading. Okay. The most important here is that in the chloride shift in the internal respiration, bicarbonate leave and chloride will comes in to have an equal exchange. And the fact that the hydrogen ion acidity help remove this oxygen, this is known as the Bohr effect. Okay. And we'll come back to the Bohr effect in a little bit. Okay, this is known as the Bohr effect. Okay, bear with me a little bit longer because we take a little break there. So I'm going to clear this. In the external respiration, then, this is what happened. In the external respiration, so let's say that here's the lung, right, where the partial pressures of oxygen is very high. And here's the blood, and you can see is that this is a red blood cell. Oxygen can go in, right? Now, if you have a deoxyhemoglobin, you can certainly, through Henry's law, for example, you can force this oxygen comes in. If it's reacted with deoxyhemoglobin, it will become oxyhemoglobin. Okay, it becomes we call this oxyhemoglobin, and it's going to kick out the hydrogen ion. Okay. Now, outside in the blood, there's a lot of bicarbonate here. All right, a lot of bicarbonate. And what you see is that the bicarbonate that is carried in the blood must be converted back to CO2 so that it can be unloaded. And so what happened is that the bicarbonate enter the red blood cell, the chloride will comes out as part of the chloride shift, right? In the internal respiration, we saw that the bicarbonate leave, right? And the chloride will goes here. In the external respiration, it's different. Bicarbonate goes in and chloride will goes out. And what happened when the bicarbonate goes in, okay, it can react with the hydrogen ion. You see here, if this is high, it's going to shift it out. So now you're going to get is that CO2 and water. And then the CO2 can escape into the lung. So then you call this CO2 unloading. Oh, sorry. This, oh yeah, this is external respiration. So it's in the lungs. So CO2 unloading. Mm-hmm. All right, so let me go back to that normal compost slide. We're going to talk about the Bohr's effect, and that will be the end. Did I talk about, we didn't talk about obstructive and restrictive lung disease? Did we talk about obstructive and restrictive lung disease? You guys remember? Okay, all right, then I won't write any equation, any question regarding that then. Okay, so a couple more slides, and this will be the end. Too bad there's no obstructive and restrictive lung disease. So if you want to know about that, you gotta take my pathophysiology class. Okay. Okay. So, oh, and then I won't ask you a question regarding um, acid and base that metabolic acidosis or res, uh, metabolic alkalosis or metabolic acidosis or respiratory alkalosis or respiratory acidosis. Okay. Now this is part of the external respiration where the oxygen is loading into the blood, so you get oxygenated hemoglobin. Okay. And note that oxygen is carried in two form as oxyhemoglobin, and then oxygen is a soluble gas. It's very this demonstrates to you the Bohr effect, right? Partial pressures of oxygen, for example, here, okay, in the tissue is about 40 millimeters of mercury, okay, which is here. This is what you have to look at. And partial pressures of oxygens in the lung is 100. It's up here, as you can see. Now, the way that this graph will look at is that each of the hemoglobin can carry 4 oxygen. If it's carried 4 oxygen, right? If it's carried 4 oxygen, then we call this as 100% saturated. If it's carried 3 oxygen, then it lose 1 oxygen is 75% saturated. Okay. And 2 oxygen is 50% saturation. So that's what this saturation means. Okay. Now the point here is that in the partial pressures of oxygen in the lung, and normal physiological pH is 7.35 to 7.45, which is this. Right? You can go up here and you see, oh, it's about 75% saturated. So in other words, oxygenated hemoglobin like this, okay, in the lung there are 4 oxygen, but when it gets into the tissue it loses 1 oxygen, right? So then it's oxygen, but there's only 3 of them, as opposed to in the lung it will be 4 oxygen. Okay. Now, what the Bohr's effect is saying is that within the same partial pressure, right? But now let's say it's more acidic, which means pH say is 0.2. So pH is here of 7.2, and you can see it's this curve. It's about 50% saturated. So in other words, the more acidic your body is, the easier the oxygen that comes out, right? So at the pH of 7.2, your oxyhemoglobin is 50% saturated. At the pH of 7.4, it's 75% saturated. So you can see how that is. So that the more hydrogen you have, increases hydrogen ion, the easier the oxygen comes off. Oxygen come off oxyhemoglobin. Okay? That's known as the Bohr's effect. And I want to talk about the similarly with partial pressures of CO2 that can lead to acidity. And again, it shows you that if this is a cell and this is the blood, so this is internal respiration again, how CO2 gets into the blood and into the red blood cell was converted to bicarbonate, and the presence of the enzyme carbonic anhydrase, it doesn't say here, and enzyme anhydrocarbon. The enzyme is carbonic anhydrase, and you can see as part of the internal respiration, bicarbonate leave, and CO2, chloride will comes in, right? So you can see here as the chloride shifts, the bicarbonate leave, CO2 comes in. The opposite of that in the external respiration, you can see is that high oxygen will comes in, and then the bicarbonate will comes in, chloride will leave. Right. So in the lung, as you can see here, and that is the opposite of it is true, is that the oxygen is going to be very high. And oxygen is going to kick out that hydrogen ion and deoxygen a little bit, for example. All right, so I'm just going to end it there. And maybe next time we'll talk about a little bit acid and base. But your exam will not have acid and base. So I'm going to stop the recording.